everybody. I'm going to talk about the Wittig reaction in this video. So the Wittig reaction is a really cool little addition to our synthetic toolbox because we're going to be able to convert ketones and aldehydes to alkene products, okay? So this is going to be a CC bond forming reaction here. And if you want to end up getting the alkene, you don't have to do any kind of weird, make a good leaving group, E2 kind of thing. You can go straight from a carbonyl, like a ketone or an aldehyde, to an alkene with this reaction. So the Wittig reaction uses a Wittig reagent. So this is technically a phosphonium ylide. Okay, the ylide just indicates that kind of charge differential there. So if we look at this, we also want to keep in mind that we do have a resonance structure available to us where we can delocalize those electrons between the carbon and the phosphorus in a pi bond. What's important to note about this one is that while this, using kind of all of the tools that we typically have at our disposal, we would say that the structure on the right is going to be our major resonance contributor. In this case, that is not correct, though, because our carbon and our phosphorus do not have good orbital size overlap in terms of the carbon orbitals are much smaller than the phosphorus orbitals, so it's just not a good overlap to do this kind of pi bond. So our major resonance contributor is actually this one. Okay, due to those orbital size issues. So when we're looking at the left-hand structure, that's kind of what we're looking at in terms of this is really showing us the picture of the reactivity that we're seeing here. So we're going to see kind of a negative charge on the carbon, positive charge on the phosphorus, and that's really how we're going to see that reaction occur. So the mechanism of the Wittig reaction is actually stuff that you've already seen before. So it's a combination of kind of cycloaddition reactions, which is pretty cool. So we're going to have our delta plus and our delta minus getting lined up. Same with the oxygen and the phosphorus. And we're going to do a 2 + 2 cycloaddition. Now I have to struggle to draw a square real quick. Okay, so then we end up with this intermediate. This is an oxaphosphatane. Hopefully I spelled that right. Okay, so from this intermediate, all we need to do is kind of fragment that apart, and we're going to get to our final product. So this was a 2 + 2. This is basically going to be a retro 2 + 2. Okay, where we're doing the backwards version. So we're going to make an OP pi bond, a CC pi bond, and then we've gotten triphenylphosphine oxide and a new alkene product. Okay, so pretty cool reaction, pretty slick little way of doing it. I would say the one thing you kind of want to keep in mind here is that the Wittig reagent, if we look at kind of how it would actually be drawn out with 3 phenyl groups on it, in terms of atom economy, it's pretty bad, just because this is all kind of waste that's getting thrown away. So you're having a lot of atoms going in that are not ending up in your product. There are variations of this that have smaller, have better atom economy, but still do the same kind of thing. So just know that there's definitely options out there, and it's kind of, there's certain good options for the situations that you're working with. So kind of keep that in mind, but something that's just going to be helpful as we do some of our paper chemistry here. All right, so to synthesize Wittig reagents, it's pretty straightforward. So all we need is triphenylphosphine and some sort of alkyl halide. So the alkyl halide that you want, we want to think about what kind of mechanism I'm going to draw right here. So if I'm going to have my phosphorus lone pair go attack that carbon, kick off bromine, okay, that will have gotten me to this structure, and that was an SN2 reaction. Okay, so that SN2 means that we have to keep in mind all of the SN2 rules, right? So okay, so our primary alkyl halides are going to work better than secondary, and tertiary alkyl halides will not work at all. Okay, so once we get to this intermediate, all we need is our final deprotonation step. And that's going to deprotonate this carbon that is now more acidic. Okay, so in this, I have N-butyl as an example here. And that has given me my final ylid reagent. So keep in mind our base, I have it listed as N-butyl for this one. Other bases that you can use. You could use NaH, Na, NH2. Okay, any of those kind of strong bases that we've seen before would be applicable in a situation like this. So this is definitely a time when we're seeing butyl being used as a base and not a nucleophile. But hopefully we can identify that because we don't really have a good electrophile here. We have more of an acid-base situation and not really any kind of carbonyls that we can go and attack or anything. Okay, so that is how we can form and synthesize the Wittig reagent using all chemistry that you've basically seen before. So the Wittig reaction does have a little bit of subtlety to it. We are not going to get too much into the why of it, but I did just want to make sure that you understood that there are differences. So if you don't have a ketone or aldehyde that is symmetric, so I picked acetone. So up here, it did not matter what alkene I was forming. It was going to form the exact same one either way, which tends to be the nice way to be able to use these. But there is kind of a selectivity process that goes into forming an E or a Z alkene. So if we start off with this aldehyde that I've got here, if we first go with using the same kind of unstabilized Wittig reagent that we've seen before, where it's just kind of an alkyl group that was stuck onto this triphenylphosphine. So this is not resonance stabilized. Okay, we don't have anywhere for this carbanion to go besides just to the phosphorus, which I'm going to put that charge there. So we don't really have anything to stabilize that charge, so it's definitely a lot more reactive. These tend to actually give the Z alkenes as your major product. Oh, nice. Okay, so we tend to get these. Okay, on the other hand, if we come in with a stabilized Wittig reagent, okay, so this one, we're going to zoom in real quick here. We can stabilize this through resonance, going up onto that oxygen through the carbonyl. So this one is stabilized. Okay, and that tends to give us the E alkene isomer. Okay, so we're going to look at something like that. So we've got the Z over here, the E over there. Okay, and there's interesting reasons as to why this is. We're not going to get into it in this video, and I'm not going to expect you to get into it in class because it is a little bit of an advanced topic. But I did just want you to know that there are ways to control it based on whether or not you've got a resonance stabilized reagent or something that's not resonance stabilized. So definitely another good tool to have. Hopefully this was helpful. And as always, let me know if you have any questions.